Okay, great. So now we're officially on. Good morning, everyone. Good afternoon. Um, so I'm very excited to today we start with the lectures of Matteo Lostaglio. Matteo, first of all, thank you for this. I really appreciate it, and I'm really looking forward to it. So please, you have the stage. Thank you.
Well, thank you, Gabriel, for the invitation. And my name is Matteo Lostaglio. I'm a researcher at TU Delft in the group of Barbara Terral. And I will be teaching you the second part of this course. So I will kind of pick it up more or less where Nicole has left it. So this is the summary of what we will be covering during the second part of the course. There will be 4 lectures. The first one today is going to be about, again, the resource theory framework that Nicole introduced yesterday. And we're going to be focusing on the physical motivation behind it and also on how do we actually use it in practice. Then there will be a class on the role of quantum coherence, and meaning superpositions of different energy eigenstates in thermodynamics. That's class 6 tomorrow. Class 7, it's going to be about a very widely used framework in thermodynamics, which is the master equation formalism. And we'll give you a quick recap of what that is and show you what's the connection with the resource theory framework and somehow how the two these two different kingdom in Nicole's map actually talk to each other. And finally, the last class will be a little bit of revision of some of the topics that also Nicole covered, but kind of in the light of this new framework that we'll be developing. And also, I will briefly talk about the issue of quantum signatures in thermodynamics. So how do we actually identify quantum phenomena within this framework? So the idea in each class is that I'm going to take a break in the middle. So 5-10 minutes break. And I will also stay at the end if there are some people that would like to ask further questions. And at that point, if some people need to head out, you feel free to do so. And I will stay for some extra questions. And apart from that, I will try to take as many questions as possible also during class, while taking the feedback as some people give, that somehow we try to balance between kind of going smoothly and stopping to give answers. So we'll try to find the right balance. And apart from that, I think I've said everything I wanted. So yeah, welcome to the second part of the course. And yeah, let me start with telling you what's going to be in today's lecture. As I mentioned, it's going to be about the use of resource theory framework. So in the first bit, I will recall this notion of thermal operations that is really at the core of the resource theory framework that Nicole introduced yesterday. And I will also mention a slightly different set of operations that one can use, which are particularly convenient for kind of developing the theory and also to move on with the second point, which is to connect physical models of thermodynamic processes with this kind of abstract framework that we introduced, to kind of have at least some schematic idea of what these operations actually can look in practice. So try to ground it in kind of well-known physical models. And so this is the second bit. And then there will be, the main part will be about this thermalization space, the thermal cone, which is actually going to be about how do you actually use this framework? How do you actually compute, extract answers, let's say, from this theory? So what kind of thermodynamic transformations can actually happen out of equilibrium? And we will see that this very difficult question can be actually reduced to something which is kind of combinatoric test that you need to do, and that you can actually check with pen and paper, or with by doing some simulation on your laptop, and you can solve relatively difficult problems using these tools. And finally, I will tell you about this notion of maximally active state. And some of you may know the notion of passive state, so we will see what this is. And finally, kind of wrap everything together by, I'm going to give you an exercise or practice for those of you that would like to do it, how to actually use these kind of tools that we introduce in this class to compute what's the optimal way in which you can cool a single qubit system. So that's the plan. And for today, so yeah, so let me start with revising the notion of thermal operation that Nicole introduced yesterday. So if you recall, the notion of resource theory, it's based around the idea that there are a certain set of operations that you can do for free, meaning in this case that you can do without spending any resource. And what we want to capture here is the set of transformation that you can do without spending any work, essentially. And so the main definition here is a state of a map that acts on your quantum system ρ. And it looks as follows. What you can do is you take your system ρ, and then you also bring in a thermal state, which is initially uncorrelated with this, with the state of the system. So this gamma E will always denote something which is actually a function of HE, the Hamiltonian of the environment. And it's just a thermal state at some fixed temperature or inverse temperature beta. So here beta is 1 over kT. T is the temperature of the environment, and T is fixed once and for all within a resource theory. So what you do, you bring in any environment that you may have devised with some arbitrary Hamiltonian HE, but at fixed temperature T, and this environment is in a thermal state. And then you couple it. So you do a very big unitary. So here you got some very big Schrödinger equation involving both the system and the environment. And this is how the unitary evolution looks like on density operators. So it's acting on left and right. And at the end of the day, you have got a very complicated state, which is correlated in the degrees of freedom of the system and environment. And the operation to give you what's the final state of the system only, it's called partial trace. And this is what it is. You're tracing away the degrees of freedom of the environment, and what you're getting is the final state of the system, which is this CTO of ρs, okay? And there is one extra constraint, which is the unitary should conserve the overall energy of system plus environment, which is gonna look like this. Or if we want to be slightly maybe more precise, there are some implicit identities. So Hamiltonian on the system tensor identity on the environment plus identity on the system tensor the Hamiltonian of the environment equals 0. So this is an overall global energy conservation condition. Okay, and this is the definition of thermal operation that Nicole gave yesterday. And I would like just to point out about this definition that if I give you an operation, so I give you a map epsilon on ρs, so I'm just telling you how your density operator, meaning the state of your system is transforming. And I'm asking you, is epsilon a thermal operation? This is quite difficult to know. Yes, I will take the question in a second. So it's quite difficult to know. Why? Because, well, in principle, you would need to construct an explicit environment and an explicit unitary on system and environment. And usually things are not, it's not so simple to kind of do this kind of construction. So this is a nice set in terms of, it's giving you a very nice intuition of what these operations are, but it's difficult to know, what is the set of all of these operations, because I would need to run through all possible environments with all possible choices of the Hamiltonian of the environment, and then all possible unitaries on system plus environment that conserve energy, and then I kind of run through all of this stuff, and I get a different channel or every time, and then the set of all these things is the thermal operation. So it's quite implicitly defined. So there was a question in the chat, why don't we take the environment very big? I suppose that the state of it is pure. Is it useful? You mean, so you can always, you can always purify the environment. I can imagine that it's all actually part of an even bigger system, and that only locally it looks thermal. So this is something you can do indeed. But then it's not obvious to me how this would be helpful in kind of, yeah, telling you a bit better what these operations are. I mean, maybe this can be a first step and then you can go forward, I don't know, but it's not obvious to me, yes. But you can do it, this is true. The environment, by the way, can be as big as you want. You can be a single qubit, or it can be, you know, a macroscopic environment. And everything is contained with these thermal operations, which is also why it contains very different things, as we will see in a moment. Cool. Okay, so if there is no other question about this, I would like to highlight two important properties, two core properties of these operations. Which is the first one, which I'm going to call T, is that the thermal state of the system is a fixed point. What does it mean? If I apply my thermal operation on the state gamma S, where gamma S is just the thermal state of the system, this is just equal to itself. By the way, the Z's are always normalization factors. So these are the partition functions that Nicole told you about last time. So in this case, this is what it is, the trace of e to the minus beta hs. So this first property tells you that the thermal state is a fixed point. So if you apply your mapping on a state that is already thermal, nothing happens. And then there is a second property, which I'm going to call S, which is maybe slightly less obvious, which is a symmetry property. Is the fixed point unique? No, not necessarily. Yes. So certainly there is this fixed point, but there could be many other fixed points. And sometimes when we do, say, master equations or other, we use other formalisms, sometimes we also assume or make assumptions that imply that the fixed point is unique. But at this level, yes, it's not necessarily unique. No worries. So, so what's this symmetry condition? Well, the symmetry condition is the following, is that if I apply my thermal operation after a unitary U, which is going to be a unitary, which is the free evolution of the system. So let me write what this unitary is. So let me first maybe write the property. The property is that these two operations commute, where this operation here is just a translation in time. It's just the free evolution of the system. And again, you got this kind of exponential on the left and on the right, because this is how unitaries act on density operators. And this is just the unitary evolution generated if you do a Schrödinger equation only involving the Hamiltonian of the system. What this condition tells you is that if you do your, first you do some free evolution for some time t, and then you apply your thermodynamic operation, or conversely, you do your thermodynamic operation first, and then you evolve for some time t. These two things are the same, so they will give you the same final state, okay? So I'm gonna leave you an exercise, which is prove these two properties using the definition of thermal operations. What if HS is not time independent? Yeah, so meaning that the final, at the end of the transformation is different compared to what it was at the beginning. Then you would need to do the kind of tricks that Nicole was mentioning yesterday, where you have to introduce a kind of ancillary system which works as a clock, which is basically simulating the fact that this Hamiltonian changes in time, which is slightly awkward. It's definitely the case that the resource theory framework is not the best one when the Hamiltonians are time dependent, I would say. Another question, does this also apply? Okay, this actually was the similar question. So I think this also applies to when the Hamiltonian changes, but the unitary at the start in the input space and output space will be different. One would be generated by the Hamiltonian at time 0, and the other one would be generated by the Hamiltonian at the final time. Another question is, does beta have to be the same as the beta? Yes, the beta is one and the same in the beta. Sorry, I finished reading for the people maybe on YouTube. Is the beta in here the same as the beta in here? Yes, which is quite intuitive in a sense, because what's happening is that the system is thermalizing to the environment temperature. So these two temperatures are the same. All right. Okay, yeah, I realize I should briefly tell you what a channel is, because there may be people here that don't know about it. So these operations here, this thermal operation that I define in this way, is an example of a channel. Okay, what are channels? Well, these are basically a much wider set of dynamics compared to just the unitary evolution generated by the Schrödinger equation. And they capture all sorts of situations, like the one that we were mentioning, where you got an environment and then you're trying to describe only what happens on the system. So the system itself is not a closed, does not evolve under a closed evolution. So you need some more general object to actually say what's happening on the system alone. And this object is given you by this notion of channel. So a channel is a linear map on the set of density operators onto itself. As we expect, we should transform quantum states into quantum states. So what should it do to actually be such a mapping? Well, first of all, epsilon, so a channel epsilon is a linear map on the set of density operators onto itself. So what does it need to do? Two things. First of all, if I apply epsilon on some matrix X, the trace should be preserved. So this is called trace preserving condition. Why? Because density operators have trace 1, because basically when you do a measurement, probability sum to 1, and this gets kind of mapped into the fact that these operators rho have trace 1. And so the output state should also have trace 1, and then you need this trace preservation condition. And secondly, epsilon maps positive operators onto positive operators, even when extended with the identity. What does it mean? So if you now have a positive operator on the system and also some extra ancillary system E, if this is positive, then also this map here where what you do is you do this epsilon mapping on the system and you do nothing on the environment. So I'm just extending with the identity on the environment. I apply it on YSE, and this should also be positive, which again makes sense because if I have, say, an entangled state and I am applying my, say, thermal operation in this case only to the system, and then there is some other state that the system is entangled with, the final state should still be a well-defined quantum state. And a quantum state, again, is a positive operator with trace 1. So this positivity should be preserved. And it's not enough to just require that the positivity is preserved only on the system. You need to also require that it is preserved when you extend it. This is something technically it's known as complete positivity. But anyway, everything we're saying is that we are defining maps that, you know, take in density operators and take out density operators. Yes, sorry, you're right. Thanks. Okay. Any question about these guys?
So there is a question on YouTube from Tanwai. So he says, I read it somewhere that if a thermal state is not the free state only, then the resource theory will be trivial. Could you please clarify this if possible?
So you mean that here you can also introduce some other state? So you're saying I'm still allowing unitaries, which are energy preserving, and then on top of allowing ancillas, which are in a thermal state, I allow also some other state. Now, some other state, which is not the thermal state of the environment. Now, if you do that, the theory is not necessarily trivial, but parts of the theory may become trivial. For example, if you allow me any state which is not thermal, then you can do every transformation between diagonal state to diagonal state that you want. So you kind of trivialize that kind of transformation, kind of the energy sector of the theory. To trivialize a theory means that you can actually do any transformation whatsoever that you want for free. Then you would need some extra states, in particular states that have some coherent superposition of different energies, so that are not diagonal in their own Hamiltonian. But to see this would require a bit more kind of technical tools.
Okay.
So there is another question. Suppose that we have two thermal states, and then you're preserving the energy of the overall Hamiltonian. Then is this also generating a thermal operation? Yes, so if the two thermal states have the same, with different temperatures. So if you allow different temperatures, then you're a little bit in the situation that, of the previous question. If you allow me two different states, so one is thermal at one temperature, the other is thermal at some other temperature. It's a little bit like if I think about it in terms of one temperature, the other state is out of equilibrium with respect to the first temperature. So, so in this sense, it works like in the previous case. It is as if you're introducing some out of equilibrium resource. And you can also think about this physically, because if you allow me two baths at two different temperatures, I can run a little Carnot engine between these two baths and extract work, and then use this work to power some other transformation out of equilibrium that I am doing. For example, I could say take an equilibrium state and take it out of equilibrium if I want, using this work that you gave me. So these are all things that you can definitely do. I mean, if you're interested in studying that kind of context, but if you allow different temperature, then you're implicitly allowing me, if you don't put any other constraint, you're allowing me to use as much work as I want. And so thermal operations try to capture operations that you can do without using any work. So that's, I guess, the answer. But cool. All right. Okay, so this was the reminder of channels. And so this then brings me to this second definition of another set of processes, which is somehow also, it's more convenient mathematically to deal with, and it's also easier to see how these processes are connected with actual physical models. So what are these set of processes? These are called thermal processes. I'm going to call them CTP. And these are all channels that satisfy the two properties that we just mentioned. The property was T and S, so the thermal fixed point and the symmetry condition. So why would we want to work with this? Well, mathematically, they are much simpler. Why they are much simpler? Well, because now I'm not giving you the operations in terms of I need to kind of run through every possible thermal state of the environment and every possible unitary. I'm giving you a well-defined set of channels with these two properties. So this is much easier to deal with technically. And at the same time is a good compromise because the basic assumptions have clear physical meaning. And the basic assumptions were, as we said, the assumption T was that if you give me the thermal state and I apply my operation, I get out a thermal state. And this is a form of the second law. So why is it a form of the second law? Because, well, imagine what would happen if this was not the case. It would mean that if I am able to do an operation that uses no work, because this is what the thermal processes are trying to capture, and brings me from a state in equilibrium to a state out of equilibrium. But then what typically you can do from a state out of equilibrium is you extract work. And then you could kind of run a perpetual machine in this way. So in this sense, this condition T is a consistency condition with the second law. And as we will see, it's this constraint that actually implies constraints on the energy. What do I mean by that? I mean that the irreversibility of energy transformations, which is implicit in the second law, will be captured by this constraint here, that the thermal state is a fixed point. And we will see how, of course. And the second one was the symmetry condition that we briefly talked about, but maybe it's good to stop 1 second more. And it looked as follows. I have my system and my environment, and then I had my big unitary, say, that does the interaction between the system and environment. And then I just let the system freely evolve for some time, T3. Okay. And this guy, the environment, I'm just throwing away and don't care what's the final state of the environment. I only care about what's the final state of the system. And what we said is that this symmetry is that this kind of configuration is indistinguishable if you do only measurements on the system from this other configuration when you reverse the two operations. So you first do a free evolution of the system for some time, and then you attach your bath to the system and you do your evolution for some, you do the same evolution as in the other case. You throw away the system, the environment, of course, sorry, and then you look at what the state of the system is. And this state is the same in the two situations. And what does it mean physically? Well, one way to think about it is that basically this symmetry captures the idea that there is no external clock at play. So in this sense, this is a time translation symmetry, meaning it doesn't matter if I apply my thermal environment doesn't know what's the time of the system. So it cannot possibly influence the system differently depending on the time in which it is applied. Otherwise, I could kind of extract time information from the final state. So this is essentially what this condition is telling you. Okay. So it doesn't matter at which time you're applying you're attaching your buff to the system. It only matters which operation you're doing. Okay, so having said this, let me also say that for the most part, it doesn't matter if you think about thermal processes or thermal operations. Meaning, essentially everything that we will be doing will apply to both cases. Just thermal processes are just quite convenient, and as I said, they have these nice properties. So we will just use the notion of thermal process also to connect with actual physical models. There is a couple of questions. What would be the problem with extracting information about time of the initial state? No, there is no problem with that, but the state of the environment is invariant under time translations because it's an equilibrium state. And also the operation that you're doing is an operation that commutes with the total Hamiltonian, meaning that also it doesn't matter when you apply this unitary, at which time you're applying this unitary, because it commutes with the total Hamiltonian, meaning it commutes with the free evolution. So there is no part in this whole thing that can allow you to actually extract time information. To extract time information, you would need something that works as a clock. For example, you would need an environment that has coherence in the energy basis so that it's not stationary under time translations. And then you could do that. So it's just a consequence, essentially, of the fact that the environment is invariant under time translations, and the unitary that you're doing is also commutes with the total Hamiltonian. Then there is nothing that can extract time information. And this is captured by this symmetry. Could you leave the system connected with the buff at all times? Yes, you could. I mean, there are many, many different frameworks that you can consider. I guess one difficulty, which is not just about in the resource theory, but in general, is that if you have a system and a buff that are coupled at all times, unless this coupling is very special, then it's even difficult to know what is that you're calling a system and what is that you're calling an environment. No, so so sometimes the coupling is very weak, so you can still kind of keep the identity of both systems separated, so the system and environment separated, or you can kind of do some coordinate change that essentially extract at some later time what is that you can call the system. But in thermodynamics, in macroscopic thermodynamics, we never have this problem, no? Because you have a macroscopic environment outside, and the system is pretty clear what it is at all times. Whereas here, everything is potentially microscopic, and so you can run in all sorts of difficult questions there. So at the moment, what we're assuming is that there is a system, and it may change. So here, not giving the most general definition, the system may change from time equals 0 to time equal final. But there is something that we can call system, and we can kind of separate from the environment. And the easiest thing to do so is that at the end, this environment gets decoupled. But yes, you can consider also more general settings. Cool. Okay, so let me go then in this second kind of section, which is about giving you a couple of models, which is useful to keep in mind, so that you have these abstract definitions of thermal operations, thermal processes, and sometimes it's difficult to see what's actually inside this set of operations. And it's good to kind of look back at some of the standard models that people have been using to describe, say, thermalizations, and see that are these models actually contained, you know, in our resource theory, because if not, we are a little bit in trouble. So one very well-known and widely used model for studying thermalization is the one proposed by David, or what we formally now call David maps, which is basically the set of the kind of quantum dynamics that emerge from a weak coupling between a system and a very large path. And then I will talk a little bit more about this kind of set, but for the time being, let me just say that for a single qubit, the kind of evolutions that are generated by this kind of interactions were worked out in this paper here. And for a single qubit, they look as follows. They are very simple. So as a function of time, your rho s of 0, so your state at the initial time, is just going to look like an exponential relaxation to equilibrium. So you're going to have a e to the minus t rho s. Of course, you can add some rate if you wish. And then you're going to have gamma s, or let me say e to the minus beta h z. Okay. So they look as a convex combination, basically, of just staying in the state you were at the start, rho s, or I should say rho s of 0, or you become thermal. And you kind of exponentially go towards thermal state. So you can see if you take t that goes to infinity, of course, the system is going to go into this thermal state. Okay. So this is, we can call this a partial thermalization. Meaning that it includes both the case where I just wait for very long and then the state is completely thermal, in principle infinite time, or I just stop at some intermediate time and I get some, you know, some mixture of the state of the system at the beginning and the thermal state. So this describes a standard relaxation, to standard relaxation to a thermal equilibrium state. Okay. And again, I'm gonna leave you a small exercise, which is prove that a partial thermalization is a thermal process. So this guy is actually a channel. If you want to double check, you can check that it is a channel. But knowing that it is a channel, you just need to check the property T and the property S. So that the thermal state is a fixed point of the dynamics. And secondly, that there is this symmetry condition that this operation commutes with the free evolution of the system. Okay. So, okay, that's nice. So we see that the kind of most elementary single qubit thermalization model is actually contained in our abstract super big set, which is good because, yes, it's very big. It's meant to capture all sorts of thermalizations. It's better, you know, it should at the very least capture these elementary cases of thermalization. Okay, so that's one situation. And now you see here, I showed you one example where you've got a super large path, and this is what emerges from a weak interaction with a super large path. But I want to show you kind of the, if you wish, the opposite extreme to see the kind of all flavors of things that are contained inside these thermal processes. One example of a model where the bath is actually not a bath. It's a thermal state, but it's a very small environment. And this is the James Cummings model. Okay, so what is this James Cummings model? Oh, sorry, I didn't see a question. Is the large path assumption only taken to ensure Markovianity? So indeed, in the derivation of Davis, he was trying to derive a master equation for the system. So this is an equation on the density operator only that doesn't show any no Markovianity, meaning memory effects. And indeed, you need the assumption of having a large path together with the assumption of having weak coupling, and then you need to look at the kind of right limits, and you get one of these equations here. I don't know if it's only taken to ensure Markovianity. Well, it is certainly taken to ensure that you have Markovianity, because if you have a small system, you don't have Markovianity typically. So the description becomes particularly simple when the path is very large, and you can imagine that information about the system is leaking into the environment, and then it doesn't come back into the system because the environment is so large, it kind of gets lost into the path. The weak coupling can be overcome by making sure that the interaction Hamiltonian and the Hamiltonian of the system commute, right? So everything I said here is just that if you consider the standard model, which makes its own assumptions, which are not kind of judging in a sense, we're just taking them as they are. If you consider the kind of operations that emerge from these physical assumptions, these are thermal processes. So they are contained within our larger set. Our larger set, it's not limited to just weak interactions. And one example is, I guess it's the one you mentioned, where the interaction Hamiltonian commutes with, well, I would make it commute with the sum of the system and buff Hamiltonians, which is what we are actually going to see in a second with the James Cummings model. You will see that you can make the coupling very large. But okay, even though typically it does emerge when the coupling is weak, I mean, as a model, because, okay, let's not get dragged into super technical questions. But yes, it's not necessary that the interaction is weak inside thermal processes, but this weak interaction model is contained inside thermal processes. No problem. So the James Cummings model, so what is it? It's a standard model of light matter interaction. And it's going to describe the interaction between a single qubit with some Hamiltonian, which we can take to be just this one, meaning that there is a gap here, which is E. So the energy energy level 1 as energy E, and the energy level 0 as energy 0. And then there is a harmonic oscillator, which is initially in a thermal state. So the Hamiltonian of the environment, it's going to look like this. It's going to be resonant with the qubit, and it's a dagger A, the number operator. So remember that the number operator, the destruction operator that appears here in the number operator is defined as follows: square root of n minus 1 n. So this guy is destroying one excitation in the oscillator, and then we'll need to introduce an analog operator that is creating or destroying an excitation in the atom. So this one is destroying one excitation from the atom. So it's going to look like this. It's taking 1 into 0. And then the opposite is as follows. And then the James Cummings model is given by an Hamiltonian, HJC. So this is the James Cummings model in secular approximation, for those of you that know about this. And it looks as follows. you got the sigma plus tensor A plus sigma minus tensor A dagger. Okay, what does it represent? Well, as you can see, this term is a term that represents a destruction of an excitation from the oscillator and creation into the atom. The other one is the opposite. You're destroying from the atom and creating in the oscillator. And these two processes happen coherently, meaning that your kind of excitations are being exchanged between the system and the oscillator in a coherent manner. So you're going through all possible superpositions of the, well, you're going through superpositions of these two different situations. And so I've got a unitary U, which is the James Cumming unitaries, which is just e to the I h James Cummings t. Okay. And now you can check that the James Cumming unitary commutes with this guy here, the sum of the local Hamiltonians. So this is 0, meaning that if I now define a James Cummings channel, as simply I take the trace over the oscillator of my couple system and oscillator in a thermal state, and I trace away the oscillator, this is a thermal operation, so in particular is a thermal process. Okay, so so here we kind of see an other extreme of the kind of processes that are included in the set of thermal processes. It's one where you've got a single oscillator and your system is a qubit and it's just exchanging energy with this oscillator. And of course, kind of energy can go back and forward, can go back from the oscillator, can kind of go back into the environment again, and you can kind of have a lot of this back and forward. So certainly this model is not one of the standard models of thermalization. I mean, thermalization doesn't really happen in the sense that the state doesn't go to some equilibrium state, but it is still contained within the set of thermal processes. Okay. So any questions about this?
So Matteo, there is a question from YouTube, but it's about the previous topic because YouTube has this delay, right? So
yeah, sorry.
The question is from Adalberto, and he's asking, are the TPs a proper subset of TOs or the contrary?
Yes, TP is a superset of TOs. So that's because, as we saw, this exercise 1 was to prove that every thermal operation satisfies the properties T and S. And of course, a thermal operation is a channel. And then we define thermal processes here as all channels that satisfy T and S. So all thermal operations are thermal processes. And I think there are special examples that have been constructed of thermal processes that are not thermal operations for Q treats. What's really not well understood is whether what you can do with thermal processes and what you can do with thermal operations is the same or not. In principle, it could still be that the set of channels is a little bigger, but you can still do exactly the same things, and this is not known. So everything that has been developed in the literature applies, all these constraints apply to both situations, so we don't know how to tell them apart, if they can be told apart.
Cool, fantastic, thanks.
Okay, so this brings me to this summary of what we saw so far. So we defined this set of thermal operations. Actually, this directly connects with the question now. You've got this set of thermal processes that is slightly bigger and easier to kind of play with and deal with. We saw this James Cummings model that is included as an example of this set of processes, which is a kind of extreme example in the sense that the environment is very small. And then we've got also the set of these Davis maps that we will discuss a little bit more in the third class in this second part. And yes, this is a very standard model of thermalization, and luckily it is included within our kind of notion. So that's quite reassuring. Yes, so this is just to give you a couple of examples that you can keep in the back of your mind. If you think about these thermal processes, you can kind of ground them in one of these different models. Okay. What are the two different black regions? The bigger one is the set of all thermal processes, and the slightly smaller one is the set of thermal operations. And then the set of thermal processes contains all of the physical models that we discussed. So all of the James Cummings models and all possible Davis maps are included inside the set of thermal processes. Okay. All right, before we take a break, let me start with this part, which is about how do we actually use the theory? Okay, now we kind of saw abstractly how it is defined. This was here and in the past lecture with Nicole. Then we now we discuss what may be physical examples that are behind it, but then what can I do now with this kind of framework? And we will start to reply to this question by first looking at transformation between non-equilibrium states, but the case where the initial and final state are both diagonal in the energy basis, meaning that the initial state is some non-equilibrium state of this form, sum over pi, and then ei. So it has energy pi with probability, energy ei with probability pi, which I will be denoting using this notation here. Okay, so this vector P is just a vector of probability, and this density matrix is actually a matrix that is diagonal in the energy basis. So if you think about it, there is it's just a diagonal matrix with zeros in the off diagonal. Sorry, I got a question in the chat. In the summary, what are the Krauss operators? I don't know where is that I mentioned Krauss operators, but yeah. So Krauss operators are a way to decompose channels. So it's one of the various representations, and you can, given a channel, you can find these operators. But sorry, I don't see where I mentioned them. But maybe you can ask me at the end of the class. So we are looking at a transformation from some state rho of 0 to some state which at the final time is going to look in general like this. So some other distribution over the different energy states. So, and again, this is some rho Q. Okay, Q is a distribution at the end. Okay, now let me define the concept of thermal cone, kind of stealing a little bit the notion, the idea of light cone. So the set of things that can happen in the future of my quantum state when I do a thermalization. And we will only be referring to populations here. So we don't talk about what happens to the off-diagonal elements, to the coherences. I will talk about that in the next class. But so let me define the thermal cone, rho of P, C of P. It's a set of all possible Qs such that there exists a thermal operation, or a thermal process, let's say, CTP, such that if I apply this thermal process to rho P, I can get to rho Q. Okay? So yes, so this is basically just a set of things that can happen, okay? The set of possible thermalizations, the set of possible non-equilibrium state that I go through while I'm thermalizing, this is all contained within this set here, okay? If I can reach it, it's contained. If I cannot reach it, whatever is the environment that I choose and the unitary that I choose, then it's outside this set, okay? Now, note the following fact. If I apply a thermal process to some rho P, what I have is a sum over I of Pi. I'm now using linearity of this operation. I just get CTP over EI. Okay? Which is, of course, rho Q. So now if I take the sandwich with some final energy, EJ, say, I get the following relation. So if I take the sandwich on the right-hand side with some energy J, I just get QJ. And here I get an expression like this. I get a sum over G of J given I, Pi, where this G is just defined as follows. Okay. So what is this telling us? So it's telling us that this Q, that it's what we want to characterize, the set of possible energy distributions that we can get at the end, can be obtained by applying a matrix G to the initial distribution. This matrix G has the form that I gave here in this equation. And now we can derive a couple of things about this equation. So first of all, this guy here is positive, okay? Or positive preserving. So it takes something positive and it outputs something positive, which means then that this matrix is a matrix of positive number, a non-negative number. Okay. Second, if I take this CTP, this is trace preserving. Remember the CTP is a channel, so these were the properties of a channel. And given that it is trace preserving, what happens if I take the sum over J of GJI? Okay. If you look at this expression here on top, I'm just taking the sum over J, but I'm taking the sum over a basis. So this is just taking the trace. And now the trace is preserved. So it's just the trace of the initial state, but the trace of the initial state is 1. So this is a matrix such that if I sum over J, I get 1, and it's all non-negative. And as you can see, what this is, it's just a matrix of transition probabilities, which formally it's known as a stochastic matrix. So it's just a matrix that tells me with what probability I'm jumping from energy I to the energy J. But that's not all, because we shouldn't forget that CTP preserves the thermal state. Okay. And now if I write this in terms of these populations, it means that if I take the Jth population, now I just kind of apply to this equation here. I know that if I input a probability distribution which is thermal, the output will still be thermal. So I get this equation. Or if you want, if I apply my matrix G to the vector of the thermal vector, I just get itself. Okay, so the Gibbs state is preserved, the Gibbs probability is preserved. So this is called Gibbs preserving. Or yeah, Gibbs preserving. Okay, so now our problem is a little bit simpler. So we've got that our C of P, this thermal cone, could be also defined in this way. It's a set of Qs such that there exists a matrix G, which is stochastic, which means it's a matrix of transition probabilities, which preserves the state gamma, and that maps the initial distribution to this final distribution. Okay, so why is this any better than before? Well, this is a completely classical problem. It's a problem about certain stochastic processes and when they exist or not. And this problem admits a nice compact answer, which is the following. It's a set of Qs such that Qs thermomajorizes or majorizes relative to gamma. Sorry, the other way around. P majorizes with respect to gamma Q. Okay, this is called thermomajorization. And it's an extension of the notion of majorization that Nicole presented yesterday. Okay, I'm gonna tell you in a second what this is and how do you check this condition. If you want a relatively simple proof of this fact, of the last equality, this equality here, you can check this archive section C. Okay. Okay, so what's the plan now? I'm gonna tell you what this extended notion of majorization is, which is the notion that characterizes the set of all possible distributions that you can reach under any thermalization process. I will tell you how you check in a graphical manner if actually this is satisfied. So if P is actually thermomajorizing Q. And then we will make some constructions and actually construct this whole thermal cone so that you can actually answer this apparently very difficult question of knowing what's the set of all possible things that can ever happen without having any control at the end of what's the set of all possible environments, what's the set of all possible unitaries, but you can still answer the question, what's the set of all possible things that can happen? So what's this thermal cone? And you can compute it explicitly, and we will see how to compute it explicitly. So I think maybe now it's could be a good time. We could have a quick break. Maybe we can reconvene around 10 past, okay? All right. Okay, guys, is there any question about what we saw so far? Okay, so let's proceed then with this thermomajorization. Okay, so as I mentioned, this is a generalization of the notion of majorization that you saw with Nicole. And if you remember, in majorization, what you had to do was to sort your vector in non-decreasing order and then check all of the partial sums and see which one was the bigger, if any of this, if any of the two vectors had bigger partial sums or not. Here we need to do something a little bit more complicated. And in particular, we need to do the following. So what is that we want to do? We want to check if some vector P thermomajorizes some vector Q, okay? The first thing we need to do is to find pi, which is a sorting such that P of pi 1 times e to the beta e to the pi 1 is bigger or equal than P of pi 2 e to the beta e pi 2, and so on. So now we are sorting again the probabilities, but now we are sorting them after rescaling each probability by its own Gibbs factor, so by its own thermal weight. So we're dividing each P by e to the minus beta e, or multiplying by e to the beta e, okay? So now this is the sorting we're doing, so not necessarily, of course, the sorting in terms just of what probability is bigger and what is not. And then you do the same for Q. Okay. And then you associate to P and Q a curve. A piecewise linear curve. Okay. Which is constructed as follows. So in the x-axis, you're just putting the partial sums of the Gibbs weights, or if you want, also the partial sums of the thermal weights. It's the same, it's just a rescaling. And on the y-axis, you put the partial sums of the probabilities, okay? And then you're just constructing, so say if in this example here I would have, say, e to the minus beta e pi 1, okay? And here I would have p of pi 1. And then I would have a second point here, which is e to the minus beta e pi 1 plus e to the minus beta e pi 2. So this would be the second point here. And then the second point here would be p of pi 1 plus p of pi 2, and so on. In this way, I'm constructing a curve for P, and in a similar manner, I'm constructing a curve for Q, which is the red one, okay? And now the condition that P thermomajorizes Q is equivalent, by definition, if you want, that the curve of P is all above the curve of Q. Okay? So of course the curve, it could be the other way around, or it could be that the curve crosses at some point, so neither P thermomajorizes Q nor Q thermomajorizes P. But if it happens, like in the plot here, that the curve of P is all above the curve of Q, then we say that P thermomajorizes Q. Okay? And now, because I think it's a bit confusing, if you see it for the first time, let's see it in action in a particular example. So I took the simplest case, d is equal to 2. My thermal vector is this 2/3, 1/3. And then I took two probabilities. P is this 1/2, the maximally mixed, and Q is this other guy, okay? What is it I need to do? I need to first order them, or beta order, as people sometimes say. So order them with respect to this rescaling with the Gibbs weights. So I need to look at not if Q1 is bigger or equal than P1. I need to see if Q1 divided by gamma 1 is bigger or equal to P1 divided gamma 1. So I need to check, I need to order in terms of the, I'm sorry, let me also not make confusion. I need to sort these probabilities in terms of these rescaled weights, okay? So I first check Q1 divided gamma 1. So this is 7/12 times 3/2. This is 7/8. Then I check Q2 over gamma 2. Okay, this is 5/12 times 3. This is 5/4. So we've got the Q1 divided gamma 1 is smaller or equal than Q2 divided gamma 2. Okay. So if I need to sort in decreasing order, 2 comes before 1. Okay. And then I need to do the same for P, because the ordering may be the same or different. So in this case, I've got 1/2 times 3/2, which is 3/4. And then I have P2 divided gamma 2, which is 1/2 times 3, which is 3/2. So again, I've got that P1 divided gamma 1 is more or equal than P2 divided gamma 2. So the ordering is again 2, 1, 2, 1. For both P and 2, the ordering is 2 and then 1, okay? So remember what I need to put here. Here I need to put this the sum of these weights, the partial sums of the weights, okay? So if I want to construct the curve for P, what's the first element? The first element is the element number 2. What's the corresponding weight of element number 2 is 1/3. So here I have 1/3. And what's the probability associated to this? What is this P2? This P2 is 1/2. So this is the first point of the curve. Okay. And then, of course, the second point is always 1, 1, because this is a, it's normalized in this way here, at least. So the second element would be P1. So this is P1, no? And this is gamma 1. And then this is gamma 1 plus gamma 2. And this is P1 plus P2, which of course is 1 because of normalization. And now I can construct a curve. And this is it. Now I do the same for Q. So for Q, again, the ordering is 2 and then 1, because Q2 over gamma 2 is bigger or equal than Q1 over gamma 1. So the first element is Q2 with its corresponding thermal weight, which is gamma 2. Okay, so gamma 2 again is 1/3. So the x-axis point is again here. And what's the y point? It's just Q1, which in this case is 5/12. Sorry, it's Q2. Okay, so the first element is Q2. So I need to draw this point here, somewhere around here. So I have this point, and then I connect with the rest. Okay, so in this case, the curve of Q is all below the curve of P. So I have the P thermomajorizes Q in this scenario. Okay, so I can use the theorem just that we mentioned just before. So Q is inside the thermal cone of P. So what does it mean? It means that there must be a thermalization process that transforms P into Q. Okay. So can you see what one such thermalization process could be that takes P into Q? Using, of course, the models that we discussed before. How do I get Q from P? Yeah, one answer is partial thermalization, exactly. So remember that what partial thermalization was doing was just doing a mixture of your state, initial state, and the thermal state, no? With a weight which was e to the minus t, no? Now, if I take this time to be log 2, I just get a half-half mixture of the state I started with, which in this case is P1, P2, and the thermal state. So this was 1/2, 1/2. This was 1/2, 2/3, 1/3. Okay, and now if you do this, you get Q. Okay. So in fact, so basically we constructed the process. But of course, so in this case, it's simple to construct the process, but in general, it's highly non-trivial to construct the process. But nevertheless, we can know, just checking, building this thermomajorization curve in a space that may be d-dimensional. At the end of the day, I just need to construct these d points and d points correspondingly for Q. Check if one of the two curves is all above the other. If it is, there is a process transforming one into the other. If it's not, I am sure that there is no process independently of the environment and independently of the unitary that I use to couple that can do this thermalization process for me. So there is no thermal process that does it. Okay. So this complicated question is being reduced to a much simpler question in this sense. So is there any question about constructing thermomajorization curves?
So Matteo, if you allow me, there is a question on YouTube, but it was from a previous topic. Again, it was a little bit of a delay. So Frank Steinhoff is asking, since the thermal state is a fixed point, can you use any contractions like Lipschitz map in some meaningful way? So he's referring to the previous part of the lecture.
So I'm not sure I know exactly what the question is asking, to be completely honest. What do you mean by, can you use any contraction here?
Yeah, so to be honest, I don't fully understand as well, but he's asking something like Lipschitz map or some kind of contraction to obtain the dynamics of the fixed point, so to speak, of the map.
So if certainly, so what is true is that because, as you said, no, because the thermal state is fixed, then if I consider any kind of distance measure between my initial state and the thermal state, if this distance measure is contractive under channels, then this will decrease under these thermal processes. So, which is capturing the idea that basically, if this is my rho and this is my gamma, these distance measures will decrease as I apply a thermal process. So this distance here will decrease corresponding to this. So this goes in the direction of monotones that Nicole was mentioning, and we will talk a little bit about this as well. So there are many monotones that you can in fact construct that satisfy these conditions, and you can use them to characterize these dynamics. It's just that these thermomajorization curves are kind of very convenient because it's a finite set of conditions that you need to check, and then you're done. So in this sense, they imply any other constraints that you may come up with.
Okay, I think that's exactly in the direction of, that he meant. If he elaborates further, then I can ask at the end of the lecture.
Okay,
Thanks.
cool. Was the partial thermalization the only way? So in this case, or maybe is there any other easy to compute thermalization that does the job? I'm not sure what you mean here by easy to compute. However, in this case, there is only one map that maps Q into P, just because of kind of counting the number of parameters. You have already the condition that the thermal state is preserved, plus you have the condition that you need to go from P to Q. And the matrix is just 2 by 2, so at the end everything is fixed. But if you go into a much bigger space, then there can be multiple maps that do the same thing. And also, even if you fix a matrix of transition probabilities, there may be different models that give rise to that matrix of transition probabilities. So yes, so yes, I don't know if I hope I replied to the question, Rafael. Cool. All right, so the break actually was before. So what's the next question? So everything that I told you for now doesn't really answer the initial question that I asked. So the question that I asked was, how do I characterize this thermal cone, the set of all possible things that can happen during a thermalization process? Everything that I told you now is that if you give me the initial state, which you know, and you give me also one fixed final state, you can tell me if that point is inside or not the cone. But this is not the same thing as kind of characterizing the whole cone, because of course in the cone there are infinitely many points, and it's not that you can check infinitely many times doing infinitely many thermal majorization curves. So the question that we need to ask is, how do we construct the whole thermal cone? Okay, and so let's start with the simplest case, which is dimension 2. Okay, and suppose, I'm trying not to confuse things, which is quite easy. Let me assume that P1 is bigger or equal than e to the P1 times e to the beta E1 is bigger or equal. So let's take an ordering. No, we could have taken the opposite. It would be the same. So the ordering, this is the notation I'm using, the ordering of P, not just sorting, but ordering with the Gibbs weights, is as follows, is 1 and then 2 in this case. Okay, and now what we're going to do to characterize the thermal cone is that we're going to construct some special states, which are going to be the extremal states of this cone, this set of things that can happen. Okay, so we're going to have that the set of all possible states that you can reach during a thermalization is actually a polytope. And for now, we just answer the question and giving you a point. Is this point inside or not this set? So this is no, this is yes. So this is what we answer so far. But now what we want to do is to characterize all of these extremal points, because if we know the extremal points, we know the whole set. Okay, so that's the idea behind the next construction. So so we need to construct a couple of thermal majorization curves. So first of all, there is the curve of P. So we assume that the beta order of P was 1, 2. So the ordering, the sorting renormalized with the Gibbs factor was 1, 2. So first of all, we need to put the e to the minus beta E1 with P1, and then the sum of the two e to the minus beta 1 plus e to the minus beta 2 and P1 plus P2. So these are the 2 points of the thermal majorization curve of P. Okay, fine. Now, consider this other curve. So what I do is to consider the opposite ordering. Instead of saying I order 1 and then 2, I order 2 and then 1. Apologies here, I think I changed the convention a couple of times. So I first put e to the minus beta e2, and then I put e to the minus beta e1, okay? So I consider the opposite ordering. And what do? I consider this point here, which is a point with the opposite ordering, and then I go as up as I can, which means here, without going above the curve of P, okay? And I construct this curve. So what is that I've just done? So I constructed, given that I constructed a curve, this curve is associated to some probability P pi, okay? What's the property of P pi? It has two properties. The first property is that it has ordering, which is 2, 1. So the other one had ordering 1, 2, this one is ordering 2, 1. So it has the opposite ordering. And second, it is maximal with respect to this ordering. What does it mean that it is maximal? It means that this P pi majorizes, thermomajorizes Q for every Q that is in the thermal cone of P with this ordering. So there is no other probability that has ordering to 1 and that it is in the thermal cone of P that lies above this P pi. This P pi is the maximal one with that beta order, with that ordering, which is in this case 2, 1. No, it's the best one with this other ordering. And this is why we constructed it in this way. We assume that it must be a curve with the opposite ordering. So I know that the x must be e to the minus beta e2, the first x. And then I went as high as possible, getting to this point here. No? Any other curve that I take with this ordering is either outside the thermal cone of P. For example, consider this curve. All right, no, it doesn't let me do it. So consider this curve. So this curve has the same ordering as the ordering 2, 1, no? But it's now outside the thermal cone of P, right? Because it lies a little bit above here, so it cannot be inside the thermal cone of P. And if I take another curve like, say, this one, well, this one does lie inside the thermal cone of P because it's all below P, but it's worse than the red one because the red one, it's all above the blue one. So the red curve represents the best possible curve that is below the black, and it has the other beta order. Okay, so why do we care about these states? Well, because what we have in this case is that the thermal cone of P is as follows: P1, P1 pi. So the two extremes are the probability you started with and the probability of this maximal distribution here. And the set of all possible things that can happen is everything that is in between. So this is the idea of extrema because, well, in this case, it's just an interval because, you know, this is probabilities, but the sum is 1. So I can represent the probabilities just by telling you what's the probability of the ground state. So this was the initial probability P1. And the set of things that can happen is defined, is just a line, is the set of all probabilities inside here. Okay. Is it more or less clear? Or is there any question about this? I'm going to show you another example for dimension 3, so maybe then, yeah, just to see if we are on the same page. Okay, let me maybe go to this example in dimension 3, and then we go back to this. By the way, this P1 here, actually, one more thing about this P1 pi. This P1 pi can be, we can actually, you know, for now I just told you graphically what it is, but we can compute what it is, because, okay, again, this is a bit messy. Sorry about this. This is just the P1 up to here plus this piece here, no? This other part. So we can write it as P1 plus, we're gonna have 1 minus P1. So this is gonna be the slope of this curve, divided e to the minus beta E1 times e to the minus beta E1 minus e to the minus beta E2, which is this distance here. Okay. And if you do the calculation, you're gonna get that this P pi is actually equal to the following. It's some matrix that looks like this, e to the minus beta delta, where delta is the difference in energy, e to the minus beta delta, 1, 0, applied on the initial probability P. Okay. So this is a special process, which we can call a beta swap, because if we take beta to infinity, which is infinite temperature, you see that this is actually just a swap. Now, if I take beta to infinity, this is doing exactly a swap between state 0 and 1. Sorry, beta to 0, temperature to infinity. Yes, I will go back a second to the question. So if you want to realize every possible thermalization, you need to be able to realize the stochastic map here. So you can ask the question, can you realize the beta swap with one of the models that we saw before? Because if I can realize the beta swap, I can go from one point to the extremal point in this set of things. And then if I do linear combinations, I can achieve anything that is in between. So something that you may, if you want, I'll leave you as an exercise, that you can't with partial thermalizations. But you can approximate it, let's say, with the James Cummings model. Okay. So there was one question. Could you explain once more, how do you see graphically the beta order, if the beta order is 1, 2 or 2, 1? Yes, so So what you do, you start with your, you have at the beginning, you just have your probability, P1 and P2, no? And then what you do is you look at the ratio between P1 and e to the minus beta E1 and P2 divided e to the minus beta E2. And you check which one is bigger, okay? Say that the first one is bigger, okay? So this one is bigger. Then you start from this one, and then you proceed with the second thing. And how do you construct the curve? You take the P1 and you put it in the y-axis, and you take the e to the minus beta E, beta 1 in this case, and you put it in the x-axis. So this is what I did here. So I constructed this point. And then you proceed. Now you only have 2 points, so everything kind of becomes trivial. But if you had many, you would proceed with the second one. You would take P2. So you would now put a new point, which is P1 plus P2. And you would put here a new point, which is e to the minus beta E1 plus e to the minus beta E2. And this would give you a second point. Okay. And what's called beta order is just the ordering of things. So in this case, I just did 1 and then I did 2. So this beta order is 1, 2. If I found the other way around, I found that P2 over e to the minus beta E2 was bigger, then the beta ordering would be the opposite. Is it a bit clearer or? Okay, cool. All right. So what happens in higher dimension? It's what happens is again the same. One needs to be a bit careful with all of the various indices and what's bigger, what's not. But at the end of the day, always the same thing is happening, and it's a purely combinatorial problem that you're solving. So here I'm gonna give you briefly an example for dimension 3. So I took a probability distribution and I took some beta order, say 2, 3, 1, no? And then I drew the thermomajorization curve of P, and I got this curve, okay? And now what I do? Now I look at all other possible beta orders that are different from 2, 3, 1. Now, for example, we can take one, say 3, 2, 1. Now, this is one possible one. So what do? I take as x points. In this case, I take x1 equal e to the minus beta E3. x2, I take e to the minus beta E3 plus e to the minus beta E2. And as x3, I just take the sum of all 3 things, no? So these are my x-axis point. And what are my y-axis points? So I'm constructing the maximal beta ordered state with this new beta order. So the x points are just these 3 because they are given to me by the beta order. And the y points are just, well, as big as I can while still being below the curve of P. So in this case, now this is the first x point, and then I go up as much as I can without going above the curve of P. So I get this point. Here is the second x point. I go up as much as possible without going above the curve of P. So this point. And then the last point is this one. And this way I constructed a probability distribution for a new state that has beta order 3 to 1 and it's maximal. Okay. So this is a curve that of a state that I'm gonna call P of pi 1, okay? And then I repeat the same, with the others, okay? So for example, another one is 1, 2, 3, okay? Then what do? Well, 1, 2, 3 means that x1 is e to the minus beta e1, x2 is e to the minus beta e1 plus e to the minus beta e2, and x3 is again the sum of all three, which is z, no? And what's a y? It's as big as I can while being below the curve of p. So here is the x point, e to x1, no? E to the minus beta e1, and then I go up, 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 till I can. I get this point. Same with the second x-axis point. I get here, and the third one is here. And then I join, all right? And then these points here are the p point, these are the p values, no? The same was here. These are the p values. I can just read them here at the intercepts of these curves. So in this way, I'm constructing many of these things. I'm constructing a p of pi 1. I'm constructing a p of pi 2. And really what I'm doing, I'm constructing one for every beta order, no? Every beta order different from my initial one. And how many of them there are? Well, it's a number of ways in which I can order 3 elements. So this is going to be 3 factorial minus 1, because the first one is the one I'm starting, so it's 5. So I'm constructing 5 of these curves. So here I did it also for another one, but it's the same for every example. And then I get 5 probability distributions, and the cone, this thermal cone is just the convex hull of all of these probability distributions. Okay, you can, if you are interested in the formal proof, you can look this lemma here. But what does it mean to be the convex hull? Well, it means as follows. No, this is P, which is where I started. This is the example I just showed you for dimension 3. Then I constructed all of these different points. Now this was the, say, the red point, this was the blue point, and there was a green one, and so on. No? 1 point, and there were 5 of them. 1, 2, 3, 4, and 5. And then if I join them all together in this, kind of the minimal simplex that contain all of them, which is the convex hull, this is the set that I was looking for. Okay, so whatever is the thermalization process that you do, no, it could be all sorts of things that are happening along the way, but it must be inside this cone. And the final point must be inside this cone. And if it is inside this cone, you know for a fact that there is a thermalization process that realizes this, a thermal process. If it is outside, you know that there isn't any. So it's impossible. There was a question just to make sure if I understood, the extremal points of the thermal cone is generated by the application of the beta swap, right? Yes, this is right. In the qubit case, this is correct. This is the map that maps you to this other extremal point. You could do the same also for higher dimension. Now you would need many maps. You would need a map that maps you here, then a map that maps you here, a map that maps you here, and a map that maps you here, and so on. No? So each of them would be some kind of beta swap thing. Does this convex hull have some particular geometrical symmetry around gamma? Not that I'm aware of. I think in general, it's the case that, if I draw a line, actually this segment is much smaller than this segment. You can kind of go on the other side of this thermal state, which means you're kind of, there is some populations that are getting inverted, but you cannot realize this inversion of population, which is as big as the one you had at the beginning, sort of. But yeah, no, there is not that I am aware that there is any special symmetry.
Matteo, there's also a question from Franklin Luis from YouTube. So he's asking, can it really be any arbitrary curve as long as it is inside the convex hull?
No. So the statement is, if you give me a point inside this pink red set, then there exists a process. So I can give you a channel. So I can give you a thermal process CTP that maps this guy to this guy. Okay. And of course, channels are only giving you snapshot information. They give you what's the input and what's the output. Then a further question would be, well, how is this channel realized in time? Like, I want the actual unitary that does the whole process. And then there would be some curve. I don't know how it looks like. No, it could even go a bit behind and then go back again. I know that there exists a way to reach it. It doesn't mean, indeed, it doesn't mean that every possible arbitrary curve that I can think about would work. In fact, there are some curves that cannot. Okay, yeah, I cannot say more. I don't know more. Yes.
Okay, thanks. That's awesome.
Can I decide whether a given process is in the thermal cone through convex programming, supposing I already know how to represent the cone? Yes. In fact, once you know so I gave you a way to compute the extremal points. Then if I now give you any other point, you can, it's a convex program to know, to answer the question, is this point inside this simplex or not? Is the only way to characterize the cone by doing all permutations, because I'm guessing that that would be computationally expensive. So it depends what is the question that you want to ask. So if you are only interested in one point, is this one point inside or not this cone? Well, you just construct the curve for that point, and you construct the curve for P, and you just compare the two curves. And then this is everything that you need to do. There is nothing else. And so this is actually very efficient to do computationally. This business of constructing all the extremal points is if you want to know the whole set of all possible points that you can reach, and you want some sort of characterization, then you need to do that. But I think in general, the number of extremal points will grow kind of as the factorial of the dimension. And so there will be many, many of these vertices. And so this is complicated. It would be very expensive quite quickly. Is it possible to calculate the volume of the convex half of all states? I mean, is there something related to its geometry and the number of states in it? Yes, I haven't tried myself. I think it's a nice question. I would imagine that the volume may be one of these quantities that must always decrease in time, no? Because if I move a bit further in time and now I'm closer to the thermal state, I would imagine that now I will have a new cone, but it's gonna be well, of course, it's gonna be all contained, no? Because it couldn't be the case now, but it cannot be any other way. So yeah, the volume will be some quantity that always decreases, from one, as you do these thermal processes, the volume of this cone is gonna decrease. It might also have some thermodynamic meaning. I think that could be interesting to check if it is related to some quantity that has an intuitive thermodynamic meaning. So I think it's a nice question. Okay. All right. Let me very quickly go through the last point because we are almost done. Also with time. So maximally active states. So let me just recall that given rho. So if you're given some rho, okay, and let me put all of the energies in non-increasing order. Then if I do a unitary, the amount of work that I'm extracting is just this difference here, the difference between the initial energy and the final energy. So now this extraction is maximal if your final state is passive. What is a passive state? Well, it's a state which has all of the probabilities, which is diagonal in the energy basis, and all of the probability are ordered in decreasing order. Non-increasing order. Which makes sense. Now you're putting the biggest probability to this smallest energy. So you're doing this because you want the final state to have the minimum amount of energy, because you want to extract as much as possible. Now, what I would like you to consider here is the opposite. And we're going to call it the maximally active state, which is a state which is ordered exactly in the opposite manner. So there is no other state in this unitary orbit that has more energy than this one. So why do we care about this maximally active state? Well, because it has a very nice property in terms of the thermal cone, which is also relatively intuitive, which is the maximally active state thermal cone is the biggest of all, meaning that the cone of this state contains the cone of every other state you obtain by doing any unitary process on it. So this is lemma 174. So in words, if you put as much energy as you can in a state, and you look at the thermal cone of that state, that thermal cone would be as large as you can. So in the set of all other possible states that you can construct by unitary, okay? So this is pretty useful when you have protocols, when you want what you want to do is to find some optimal, and you have a sequence of unitary and thermalization processes. So what's an example of such thing? Well, this is a set of cooling protocols called heat path algorithmic cooling protocols. So what are these protocols? These are protocols whose aim is to maximize the ground state population of a quantum state by a sequence of unitary interactions and thermalizations with the environment. So if you want to consider a simple case, you can consider the following, where you got a state that comes in, and you can take this to be a single qubit. Then you do a unitary, or you're allowed to do a unitary, and then you do a thermal operation or a thermal process if you want, and you get some state out. No? And what I'm asking here is to find the unitary and the thermal operation or thermal process that minimizes the ground state population. Okay. How is this maximally active state going to be useful? Well, remember that if the unitary is making the state maximally active, then the thermal cone is the biggest. So the set of things that can come out of your thermalization process is the biggest. So that notion is gonna help you choose the unitary. And then what we saw in terms of constructing this convex set is gonna tell you how to solve the problem of what's the best thermalization in terms of maximizing the ground state population. So that's the first question. The second, what happens if we repeat this this step which is optimal for this that you found that is optimal. What happens if you repeat it many times? How does this ground state the probability of being in a ground state scale with the number of repetitions? What you should see is that you can increase the ground state population exponentially with the number of times that you repeat the step. So I thought this was a nice example, not the simplest, but it's nice because it kind of uses all of these different things that we saw in this class. So now it's 5, so I will finish here. As I said, I will also remain for another few minutes, so for people that would like to ask any other question, but of course for all of you that may have to go, please go, and thank you for listening.
Awesome. Thank you so much, Matteo. Maybe I can kick off with the questions. There's a question from YouTube from Tanmoy. So he's asking, so for an arbitrary d-dimensional case, there will be d factorial extremal points for the set of thermal processes, right?
So I'm not so I'm not 100% sure that every, so there are d factorial states that you're constructing, or d factorial -1 that you're constructing using this method. Not all of them are necessarily extremal, but certainly they contain all extremal points. So the statement is that there are at most d factorial extremal points, but they may be less.
And there's also a follow-up question. So since TO is a subset of TPs, are the set of TOs also polytope?
Yes, actually, what's also convenient in terms of now, I took the approach of just using TP, is that actually the set of, here I define the problem in terms of stochastic matrices, no? I need to know the set of possible final states you can reach with stochastic matrices that preserve the initial state. So the same is true for thermal operations and thermal states and thermal processes. So they are exactly the same. They have exactly, for this diagonal, they are exactly the same. They have exactly the same sets. So again, as I was mentioning at the beginning, for the most part in all of these classes, you can think about one or the other. It's going to be the same.
Cool, cool. Okay, I guess from YouTube so far, these are all the questions we have. I don't know if anyone here in the Zoom room has any other questions.
So apologies, I made a bit of mess with the indices. That often happens with thermomodularization. I will then send to Gabriel a corrected version of the notes. So I will double check all of the indices, so I will not confuse you further.
Cool, cool.
We could send to you the exercises. Yeah, you could. Maybe we can do as also Nicole did. We can maybe briefly discuss them at the beginning of the next class. So maybe you can also do them, and then I will ask if someone wants to tell her or his solution, and we can briefly discuss it at the start. But if you have some doubts, you can also write me, of course.
Oh, maybe there's also another question from YouTube from Franklin Luis. So he's asking, what would trigger one beta ordering not to convey an extremal point? Is this known?
Yes. No, I don't know, to be fair. I don't know if, so it should be something like that there is one of these points. I mean, maybe you get that one of these points is maybe collinear with some other extremal point. So there may be the generous situations because, kind of, if you have one qubit, it's just a line, but then if you go higher and higher, you have a very super big simplex, and you may have more complicated situations where things are degenerate in some small subspace.
Right.
But to be honest, I've not thought in detail about this question.
No, cool.
In this case, as you see, there are 5 as we expected, or 6 counting also P. So in this case, everything is working fine, but yes, in higher dimension, I don't know.
Okay. So I guess if there are no other questions, Matteo, we end up here.
Thank you very much.
Yeah, okay, awesome.
See you tomorrow then.
See you tomorrow. Thank you, everyone. See you all tomorrow. Bye-bye.
Thank you. Bye.